Hello and welcome back to the Renewable Energy Technology course. I'm Miro and this is a continuation on the lecture series on wind turbines and wind power. We are still at lecture 1, Basic Aerodynamics, Major Types and Operational Principles of Wind Turbines. But now we will very quickly actually make a review on some important practical fluid dynamic, aeroelasticity and typical characteristics of wind turbine issues. Very important, but we are forced really to very quickly run through the material. Quick reminder, lift force in wind turbines. All kinds of turbines actually would be using the lift force as long as there is an aerodynamic wing profile working as the blade in each stage. In wind turbines though, especially if we look at the tip of the long blade, it would be approximately looking like this. It translates or it travels in this direction. Even if the air is completely standing still, the fact that the blade travels through air would mean that there would be a relative velocity of air u towards the blade. The real wind comes from here, directly towards the belly of the blade or towards the pressure side of the wing profile. And it's comparatively low speed wind compared to the speed of translation of the blade. The forces, lift and drag. The drag is always parallel and directly in the same direction as the resulting vector force of the apparent wind. And the vector is the sum between the real wind and the relative wind of blade translation. The lift is always perpendicular, normal, 90 degrees, right angle, to the vector of the apparent wind. And the angle here is usually denoted as angle of attack. This is relevant for all kinds of wind profiles and all kinds of blades. However, here, notice that still the lift force is the propelling force for us, but it's only the projection of the lift force on the blade of on the plane of rotation that would actually propel the blade. The drag force projection would be the stopping force. And the lift plus drag force projection on this axis here, axis Y in our example, is just the bending force on the blade. The thrust that the blade, then the structure and the foundation of the turbine should withstand in order not to tip over. Lift force should be produced as much as possible so we could convert any energy from the wind into mechanical power. The rotational wake, we already looked at it very quickly. Please don't forget that it shows us that there is a practical limit far below the Betz limit when a wind rotor is rotating slow. So the fact that actually the blade, especially towards the root, is curved, if it's properly dimensioned and properly facing at the proper angle of attack, the apparent wind, would mean that if the wind is coming really from here, it would be deflected inevitably when it reaches the blade and when it exerts pressure or forces on it. The rotation of the wake behind the turbine means that there are losses, or this is the representation of losses. Energy has been converted not into rotor rotation or mechanical power, but useless rotation of the air wake behind the turbine. Slow rotors are far less efficient than faster or quicker going ones. In very long blades, the tip section is actually the most productive part and the most efficient part, while the root section is very important. It should be mechanically strong to carry the rest of the blade and the enormous forces there, but it is not very productive aerodynamically. And it produces the largest amount of wake, the root of the blade. Very nice example that the power coefficient and thus the aerodynamic efficiency of a rotor actually is a function of the tip speed ratio. The faster the rotor rotates, the more efficient it has the chance to be. And this graph very nicely represents what happens with slow-going turbines. For example, if we have a rotor that operates at an optimum tip-speed ratio of 2, it has the chance to be maximum 50% efficient. And if we go down to even slower rotors, for example, drag turbines that cannot even reach the actual speed of the wind because otherwise there would be no forces on the, or useful forces on the rotor, they have no chance really to be efficient at all. Very nice photo, you can find it out there on the web. It's actually from the Danish offshore wind site Horns Rev. Very, very nice. Wet air meeting the rotor, starting to expand, you know, the streamlines of air behind the rotor, which means it cools down slightly. The high moisture content condensing in the wake, and this is much better than any lab can visualize what happens after that. The wake expands, proceeds further away behind the turbine, turbulence starts to appear towards the edges at the boundary layers. And in this particular case, actually, badly, it hits directly the next row of turbines, something that should not happen. It has happened here that the wind comes from the most undesired direction, directly along the row within the matrix of the wind park, along the row of turbines. So each next turbine is severely obstructed and unproductive, that is, working inside the wake of the turbine in front. The profile losses are usually referred to or relevant to the drag force in the all kinds of solid objects that would work in an aerodynamic or fluid dynamic field. When it comes to wind rotors or wind turbine blades, they would always have a certain drag, of course. The target is that we use wing profiles or blade profiles with minimum possible drag, and we operate them at maximum possible lift. The ideal ratio of lift coefficient to drag coefficient should be well close to infinity. In reality, as soon as it is close to 1,000 or at least more than 100, it's very good. So 1,000 times difference between lift coefficient and drag coefficient. We can easily neglect the drag on a well-streamlined rotor. But as soon as there is drag, that would be the friction between the fluid and the solid object, or the solid profile of the blade, the drag force needs to be accounted for. So these drag forces actually would mean that as soon as the lift-to-drag ratio decreases, the fast-going, quick-going rotors are not as efficient as they would have been if there were no drag. If the rotor starts to rotate now, or if the intrinsic tip-speed ratio, the optimum tip-speed ratio for a rotor is very high, meaning that it's very slow going, very high speeds along the blades, well, the drag force would be enormous, and it would start losing the positive force or the useful force more and more towards the higher speeds. So there would be some kind of an optimum, depending on how big the drag force is, somewhere here. And that's exactly where the actual real turbine operate, between tip-speed ratios of 5 to 10. Hoping that usually the lift-to-drag ratios are approximately 100. As soon as they're below 100, this is a problem. The optimum you see is somewhere here, around 7 tip-speed ratio. Tip loss is a three-dimensional effect. As long as we can consider the wake, the rotational wake, as a two-dimensional effect, the tip loss definitely would be a three-dimensional issue. It might be difficult to explain, but actually not difficult to understand as soon as you see the whole picture, even if I tried here to draw it not so good. It's a pathetic attempt. What happens, looking at from the belly of an airplane wing or any kind of common wing, air flows along the wing, both below and above it. The wing finishes somewhere. It has a finite length. Exactly at the tip of the wing, there is no border in between the pressure side below and the suction side above. So there is nothing stopping really the pressurized fluid from below the wing to bypass the tip and to reach towards the suction side. So there is a flow developing here, constantly attempting to go around the tip. The entire flow field around or below the wing tends towards, or these streamlines would start tending towards the tip, while the opposite would happen on the top, on the suction side of the wing. Approximately the same thing would actually happen with a wind turbine blade, especially thinking about the fact that the lift forces are very high there. The difference between pressure side and suction side is enormous, even if most of that force is just resulting in thrust bending the blade. Still, those forces are enormous. As soon as the blade finishes abruptly and there is no obstruction to the flow, the tip loss will occur. It can be represented, and it is represented usually with empirical coefficients, simply showing that the lift coefficient decreases towards the tip. Besides that, there is a rotational, well, turbulent, I should say, wake appearing behind the tip. When the tip of the blade travels through the air, it leaves a pressure differential behind it so that there is a swirl constantly developing here and being entrained in the wake and acting actually on the boundary layer of the rotational wake. What can be done to decrease this loss is actually to involve some kind of obstruction to the flow so that the air or any other fluid cannot easily go around the tip. Please read the text. That's how we have so much text on the slides. It is self-explanatory and can be used for home studies. This is some good examples of, decisions on how to decrease the tip loss. And the common decision is to use a winglet. The winglet is simply specially designed tip here, usually curved tip, which simply stops or attempts to stop the flow by passing the tip of the blade from below towards the upper side. Any kind of flying structure that relies on high lift, especially at slow speeds, would definitely need a winglet towards the tip so that proper high lift force develops along the entire blade. If the blade or the wing is super long or infinitely long, the tip loss would be infinitesimal. So the tip loss relative effect would decrease with increasing length of the blade. But if you want to have a short blade with maximum performance as in a heavy airplane, you would definitely choose to have a winglet. An Airbus in the standard way uses winglets in more or less all of its passenger airplanes. Boeing didn't. But recently you would see those big and funny aftermarket winglets attached to almost all of the Boeing air jets. And the new designs definitely choose to have winglets directly from the drawing board. Can a wind turbine blade have a winglet? Of course it can. It's just a matter of decision. How exactly it is engineered, that's a different story. But there is a wind turbine blade, large-scale commercial wind turbine blade, that attempted to use a kind of a winglet. It's simply a curved tip. It also helps with decreasing the noise, which in some cases is much more important. But it also definitely acts as a winglet, decreasing the tip loss. However, the winglet in a typical wind turbine situation is deemed to be unnecessary, or just a unnecessary complication of the blade. definitely making it more expensive, maybe more vulnerable also to stress, fatigue, and other loads that can decrease the life of the blade. You can see some winglets also in small turbines. These are some examples here. Well, just a flat end for the blades, hopefully working as a winglet. It is actually quite rare, though, to see winglets on any wind turbine, especially in large modern, large rotor diameter machines. The size or the length of the blade actually shows that, well, the tip loss is relatively small. It's no point dealing with it. Rather, just having a simple, more solid blade is better. That's one example of the relative influence of the tip loss. If we have a single blade, the relative influence might be more detrimental. If we have many blades, it wouldn't be that high. Again, the tip loss will act so that when it starts to represent itself more and more, the performance, the actual performance of the windmill would start decreasing more and more from the optimum possible, theoretically possible one at those parameters. Quick overview of the aerodynamic performance and types of windmills. Now, this is a very important issue here, and the other teacher in the course will also stop at this. You are welcome to explore this type of diagram. There are several versions of those available. We can order the typical types of windmills like this. First of all, the tip speed ratio, the optimum tip speed ratio plus the span of tip speed ratio in which they can operate. Then the power coefficient, definitely, which is a kind of an aerodynamic efficiency, but also the moment coefficient. So this is the ability of the rotor to produce torque, especially at low RPMs, so when it starts to accelerate from standstill. That's a serious issue for wind turbines. You can see here, please explore this slide, that the most important types of windmills just ordered and the typical speed of their operation and how they look like, of course. The three-bladed rotor would usually operate around 5, maybe 6 tip speed ratio value, while the two-bladed one is intrinsically faster going. Slow rotors, not very efficient. Low tip speed ratios. But especially the drag force rotors and the slow-going multi-bladed ones, they are very, very, they are able to deliver strong forces already at startup. And this is the most important feature for those. Fast-going rotors, they don't have much of a starting torque. They should be allowed to accelerate without the load, otherwise they would never start up. Or you should forcefully start them up somehow. Some of the very old small windmills could use the generator as a big motor, just starting to propel the turbine like a big ventilator, like a fan, until the aerodynamic lift force develops and the rotor catches on and is able to produce power. Very important figure, please reflect about it. The starting torque is connected to the solidity and the typical tip speed ratio span of all kinds of turbine rotors. A low solidity, quick running, typically lift force rotor does not have a very high starting torque. However, it's very efficient once it starts rotating at the optimum tip speed ratio. It is very aerodynamically efficient, so we would like to use those turbines for electricity production. High solidity, slow running, multi-bladed, whether lift or drag force devices, they are very good for driving heavy loads, especially at low speed. And they are able to start or to start up already from standstill under load because they do have a high starting torque. Just think that the wind actually acts on many blades simultaneously, while the few-bladed rotor, it needs to rotate inevitably much faster in order to catch all the wind passing through the cross-sectional area. Quick summary. The two-dimensional and three-dimensional effects plus the drag force itself actually decrease the aerodynamic performance of real wind turbines in real conditions. Decrease it so much that the Betz limit is an unreachable goal for any actual machine. Plus the fact that the Betz limit itself actually limits or cuts off the possible performance almost to half of the available energy in the undisturbed wind flow. Efficient wind turbines should definitely use the lift force if they need to be efficient, and should use quick running rotors with few blades. Starting torque is important if the device is supposed to operate constantly loaded, and if it should be able to start on the load or to start up from standstill while the load is constantly connected. This is the typical case of a wind pump. We are coming back to those turbines later on. Thank you.